Welcome to Study Loop.
Okay, this is chapter 11, section problem 70, and this is the part in the chapter where things start to get a little bit longer. So what we have to do is calculate the amount of heat that's evolved in kilojoules for 1 mole of steam at 145 degrees Celsius to ice at minus 50 degrees Celsius, 50 degrees Celsius. And they give us the heat capacity of the steam is 2.01 joules per gram per degree Celsius, and that of ice at 2.09 joules per gram per degree Celsius. But that is not all the information that you even need. You need the specific heat of steam, liquid, and ice, and those are 2.01, 4.18, and 2.09 joules per gram per degree Celsius, all respectively. So, also you need the delta H of vaporization and fusion, because this is the part where you have to calculate the heat that's required to. This is a 5-step process. So it's the heat required to go from 145 degrees Celsius of gas to 100 degrees. And then we're going to plateau. It's going to convert from a gas to a liquid. And this is fusion or condensation in our case. And when that's all done, then it's going to be a liquid. The temperature is going to change from 100 degrees to 0 degrees till we get to the freezing point. And then after all of the water has frozen to ice, then the ice is going to decrease from 0 degrees. Oh, we already did that one. To what, minus 50 degrees. And the way that this works out is this Q1 plus Q2 plus Q3 plus Q4 plus Q5. And each of these basically follows the general formula for specific heat is like Q is equal to MCAT. That's how I think of it most of the time. So like heat required is going to equal, M is mass or moles or whatever, but we'll say mass here. Mass times specific heat times the delta T. Q is equal to MCAT. It's a really easy way to remember that. But when you're going through the phase changes, well, okay, then there's no delta T, but you still just, plug and chug. And the key here is when you're doing your equations to match up the units. So like they gave us 1 mole of steam. So, when I was doing my math, well, I noticed that these are in grams. So you have to go from grams to moles every time, right? Or moles to gram. There's 1 mole. There's 18 grams of water per 1 mole. And you keep going on and so forth. But this is the part where you gotta add these all up individually, and I can go through those right now. Okay, so the first one that we got to do, like I said, is going from the hot gas to a little bit of a colder gas. So we started off with 1 mole of steam, and then if we can change that into grams of steam by multiplying by the molecular weight, 18 grams per mole. If we look, then our units would be grams. Then we use the specific heat of steam, and that's 2.01 joules per gram per degree Celsius. And then if we multiply that by the change in degrees Celsius, which is we're going from 145 to 100, so the change delta T is 100 minus 145. This should always be negative if you're going down in temperatures. So we multiply these all up, and you always want to check the units, make sure they make sense to you and that they cancel out along the way. And yeah, this is going to be 1628. And that's just the heat from going from hot gas to colder to less hot gas. Then once it's all 100 degrees Celsius, then we have to go through the condensation equation. So, again, we're dealing with 1 mole of steam, and the delta H of vaporization is 40,700 joules per mole. Again, this is in moles, not grams, so this number should make sense. There's a larger value. And also, the nature of this process is different. We're not changing the temperature anymore. We're changing the state of matter. So the fact that these values are so much higher than the other ones, it's because we're breaking bonds, hydrogen bonds, if we're going from a liquid to a gas. So that should be a huge value. Okay, so we do that calculation, and then we'll add that to the Q from the liquid, which again, is 1 mole times 18 grams per mole times 4.81 joules, joules per grams per degree Celsius. And then we multiply that by negative 100 degrees Celsius, which is the change in temperature going from 100 degrees to 0. We'll add that to the Q from freezing, right? So again, 1 mole of steam times 6,020 joules per mole. And again, it's this says vaporization, but this is really freezing. Oh, geez. Okay, that is the right value. So that's going to give us the amount of heat from freezing. And then the final thing that we have to add to it is the, I was copying and pasting these. I do apologize. Okay. So we add all these up and we get the values for the total amount of heat required. And that's minus, 57,753 joules, or minus 57.8 kilojoules of energy. And this is kind of the way that you have to do it. It's a long process. Usually if you, this will be like one big question at the end of a test, or, this will be a big lab. So get used to, figuring out how to do Q1 plus Q2 plus Q3 plus Q4 plus Q5, because this is going to be on a test. So good luck.